Okay, we're recording. All right, let's enter the password of the user and get started. So we go into the folder of the demonstration example and ps2. So this is the whole, all the files are in your zip folder I have uploaded on Teach Center. So you can actually follow the demonstration example step by step. Okay, first of all, we need to define the geometry. And again, we use trellis for this purpose. And the geometry, the journal file is already provided. So again, like in the last demonstration example, first of all, we create the vertices, then we create curves from these vertices, then we create the regions, like the kind of volume regions, which are surfaces in our case. Then we assign names to the regions, merge the regions where we want to have a conforming mesh, and mesh all the stuff. All right, going from this bottom-up approach is kind of a tedious task because you really have to enter all the coordinates of the nodes and then connect the nodes with curves, which can be quite tedious and time-consuming. And the reason we have it that way is because we created the script automatically. So we created this journal file with a script. So we were actually meshing this geometry in Gmesh before we were using Trellis, and we just wrote a converter script for the Gmesh script to Trellis. That's the reason why we are using this totally bottom-up approach. If you're doing it on your own, or you want to mesh a more real-world geometry, you can use. I think I've already shown you in the Heat 2D demonstration example that you can create your geometry actually via the graphical user interface. So instead of defining all the vertices here, you can maybe start by creating lines. So you enter these coordinates here in the graphical user interface. So you can skip the whole create vertices section here and start with the curves. Or we go one dimension higher and create surfaces right away in the graphical user interface. And the reason and the way we can create surfaces is shown here in this drop-down menu. So we can create surfaces from bounding curves. So if we construct the curves, the curves first, closed curve loop, then we can fill this closed curve with a surface. Or we enter the width and the height of the rectangle straight away. For example, we want a rectangle with width 0.5 and height 1 in the set plane. Just click apply, and we have a surface. We don't have to define node, connect the nodes with lines, and then define the boundary and bounding curves and create the surface. We can create simple surfaces without going all the way through vertices and creating lines, filling the curve loops, which is a fast forward approach. And we can copy this journal command which created our rectangle. We can copy that and maybe add it in our journal file and go from here. So in our case, you don't have to construct it all over again. We already provide you with the journal file that creates the geometry, so we can use this geometry. Maybe in some further future homeworks, you will have to create a journal file all by your own. So then you can use the fast forward approach. But in this case, we give you the journal file. You simply have to execute it, and you get the geometry with the defined regions and blocks and node sets we need for the boundary conditions. Okay. And this is also a slow approach. As you have seen, creating the vertices, connecting the vertices with lines, filling that stuff is slow. Creating that rectangular surface via the GUI or using the fast forward approach is faster anyway. All right, what have we got here? We have 3 blocks and 2 node sets. So the first block is the air domain, as I've already shown you in the PDF file. This is our air domain, the upper air domain and the lower air domain, the coil region, and the material region, which is actually the plate consisting of different materials. All right, regarding the boundary conditions, we have defined 2 node sets, the vertical and the horizontal boundaries, boundary curves, boundary lines. All right, that's it from the trellis part. We have exported our geometry in the CDP format as geometry-ue.cdp. Now we can close trellis and start editing our XML file. So what have we got here? We have our CDP file. Okay, now let's open Eclipse and observe the coil.xml, which defines our simulation. Yeah, what I was experiencing the last few days, that the virtual machine is getting slower and slower, and I don't really know why. So from time to time, just shut down your virtual machine. Most of the time I use save the machine state, but this seems to fill up some space and decreases the performance of the virtual machine. So I would recommend that you use this button, power off the machine, if you want to reset everything. All right, then let's load the XML file. I'm not sure if this is the correct one, so I'll just delete it from here and load it again. So right click, new file, and share coil XML. And you're already familiar with the first sections. So the file format is the same as last time, and the same as you're using in your homework. We define the geometry, define the material file, and then we can define variables. I'm not sure if we have already been through defining variables in the last example. I'll just repeat it again. We can define certain strings. So this is a this is a string I, string N, string capital A, and assign certain values to these strings. So in our case, we want to prescribe a current of 40 amps through the coil, and the coil consists of 200 coil windings, and each coil winding has a wire cross section A of 40 E minus 6 meters, square meters. And we'll use this string variables in the coil definition in a minute. Before that, we need to assign the materials to the different regions. So the air domain, of course, it has the material air. The coil domain also has the material air, because we don't want to have a relative permeability in our coil definition, especially when we're dealing later on with magnetic dynamics simulation, where we have to consider eddy currents. So if we have a stranded coil, consisting of, for example, Litz wires, we do not consider eddy currents in the coil. So we simply assign the material air to the coil domain in order to prevent eddy currents. Like in this magnetostatic simulation, it's not necessary because we don't have eddy currents. But later on, it will be necessary. All right, then we have the region material, so that the plate on top of the coil, consisting of the nonlinear material, and the material we're using is called iron table. And now we want to find out what that material is. So we open the mat2.xml file, which I've already opened here. This is the air material, this is iron analytic, and this is iron table. That's the material we're using. Maybe if we have time, we can also use the other material definition. So what we're defining here is, again, the electric conductivity, which is considered to be linear, and the magnetic permeability here in this section. And we have to define a linear permeability as well as a nonlinear permeability. And we need the linear permeability either as a starting value for the nonlinear iterations, or if we don't want to use the nonlinear property, we can define it in the XML, in the simulation XML file later on, if it's nonlinear or if it's linear. And if it's linear, we don't use this nonlinear section anyway. All right. What kind of nonlinearity are we considering? So we have our pH curve, our commutation curve or anhysteretic curve, in a file called ph.fnc, where we have the B and the H, like the magnetic flux density and the magnetic field strength relation, which forms the pH curve or the commutation curve. We have these data points in a file called ph.fnc. Now let's have a look at that file. Let's say vim ph.fnc, and the content of this file is simply two columns, where the first column is the magnetic field strength and the second column is the magnetic flux density. So these are the data points, the XY data points. Now let's briefly plot the pH curve. Let's do it with GNU plot. Plot ph.fnc. That should work. Yeah. Okay, what you see here is on the x-axis the magnetic field strength, and on the y-axis the magnetic flux density. And these are the xy values forming our BH curve, or anhysteretic curve. So that's our material relation, our nonlinearity, nonlinear permeability. So the permeability, the quantity or the parameter we are considering is the derivative of this BH curve. So mu is dB over dH. All right. So here we're defining the table where our nonlinearity is stored. You don't have to bother or consider these 4 lines here. These are just these just have numerical reasons. So just leave them as they are. All right, this is one way to define a nonlinearity, to define the permeability over field strength relation via a table. The other possibility is to prescribe actually an analytic function. And this is done in this iron analytic material, where we directly prescribe the relativity via this lengthy expression here, which is also which delivers the same relativity curve as we would get from the table, the lookup table. What you also have to define, if we consider the analytic version, is we need to define the derivative of this expression here. So you don't not only have to define the nu as a function of b, but also the derivative of nu with respect to b. So we need to define 2 things. All right. Now we're using first shot. We're using iron table material. Now let's go back to the simulation XML file. So we're using iron table and define our sequence step as in the last example. We have a magnetostatic simulation, so a simple curl problem with the magnetic with the impressed current density on the right hand side. Okay, and now here in the region list, we define in which regions we want to solve our problem. And that's the location where we decide if we want to simulate it with a linear or a nonlinear permeability. So if we want to use a linear permeability, we simply define regions air, material, core, as we were doing it in the magnetics linear example. If we want to use the nonlinear permeability, we have to add a nonlinear IDs tag. And this tag has the name nonlin, which corresponds to the nonlinear permeability definition here. So we to have the connects, this identifier here links to this tag, and this tag tells you which quantity is the nonlinear quantity. Maybe we can have a look at different nonlinearities we can consider. So we can consider, like, the hysteresis version is still in development or under development. So it's not even a beta version, it's an alpha version actually. And we can also consider magnetostriction as a nonlinearity. But in our case, we're just using nonlinear permeability and define this material called material has a nonlinear permeability. And then it uses the nonlinearity, the nonlinear tag here in the material definition. Okay, that's it regarding the nonlinearity. Then we need to define the boundary conditions as we had last time. So we define a flux parallel boundary condition at the outer boundaries. And the other new topic is the coil. And in our case, we're using a current-driven coil. I think it was already a topic in the lecture. So the quantity we are prescribing in our weak form is the impressed current density. And so it's a density which is homogeneous across the whole cross section of our coil. So we're not considering the resolved Litz wires or the actual wind coil windings. We're considering the homogenized cross section, where we say we have n coil windings. Each winding has a current of 40 amps that we defined. So our total current is current of one wire times number of wires in our domain. And here we define the cross section of one wire. And then CFS calculates the current density internally. So you don't prescribe a current density, you prescribe the total current, or you define the total current here in the XML file. Okay, the coil has the ID coil 1. It's a current-driven coil. We can also define a voltage-driven coil, where we also have to define a resistance and some other more advanced definitions, but here we just stick to the current-driven coil, and we define the region which is a coil. And in our case, our coil region has the name coil, so that's our definition of the coil. And the current points in set direction. I'm not sure which direction is the set direction. Let's have a look at the mesh once again. Okay, now it's correct. The set direction is actually the phi direction in a cylindric coordinate system. It's okay. Yeah. So the current is pointing in set direction, and since we're using an axisymmetrical formulation, it's the phi direction actually. Okay. Then, as we already had last time, we want to store the magnetic flux density, the magnetic field intensity, and the actual solution quantity, the magnetic potential. And the next new thing regarding the nonlinearity is this section here, the linear system. That's also new. We did not have to consider that in the previous example. Because here we're defining the actual solution method we want to use to solve the nonlinear problem. And if we are using the magnetic PDE, so in 2D we're using this so-called magnetic PDE, which uses nodal finite elements to discretize the H-curl function space. We can use two different nonlinear methods, solution methods. We can use Newton or fixed point iteration. If we are using the magnetic edge PDE with edge finite elements, we have only the fixed point iteration currently implemented. But this will be a topic for future exercises. Okay. In this case, we're using Newton's method to solve for the nonlinearity. And maybe you have already considered it in the lecture. We need a so-called line search approach, additionally with this Newton approach. And here we're using the minimum energy approach. Yeah, I don't have to think too much about that. The important thing is the stopping criteria, or are the stopping criteria. So we have two stopping criteria, an absolute stopping criteria and a residual stopping criteria. And a rule of thumb when you're using OpenCFS is to use the same value of the stopping criteria for the incremental and the residual stopping criteria. And we also define the maximum number of iterations. So if you do your nonlinear iterations and you do not reach your stopping criteria within 100 iterations, then the simulation stops. But this is just in order to prevent infinitely long simulations. Okay, and yeah, you don't have to, just leave the other sections as they are. We're using a direct solver for our forward problem. It's called the Paradiso solver. Okay, now let's execute, or let's simulate this XML example. So we are in the correct folder. We type CFS coil and simulate. And we have simulated the nonlinear problem. And now we want to observe the number of iterations we needed to converge towards our stopping criteria. And the informations of the simulation are stored in the info.xml files. So the info.xml file has the same name as our simulation XML file, in our case coil, but with the file ending .info.xml. So let's open this XML file. We just use gedit, a simple text editor, because we do not need to modify the file. We only want to look at the tags. Okay, this info XML file contains all information of your simulation. So it contains, implicitly contains the simulation XML file, different regions, and a lot of additional information. Then the information we need in the nonlinear regime is at the very bottom of the info XML file, here in the nonlinear convergence tag, where we see the iterations and the corresponding residual error and incremental error, and also the parameter, the kind of optimal parameter for our line search parameter. But the important values are incremental error and residual error. And in our case, we see the error is decreasing, which is good, and we're reaching our defined stopping criteria in the fourth iteration. Now let's have a look at the result. Let's open ParaView, -- Meson, results coil. We don't want to look at the solution at the boundary, so we only check air, coil, and the material domain. and look at the magnetic flux density, for example. Okay, looks plausible. We have a maximum magnetic flux density of 1.1 Tesla occurring here at the bottom part of the plate, where we expected the solution to be high. Okay, in order to compare this nonlinear simulation with the linear version, let's rename the result. So let's rename this coil.cfs to coil nonlin.cfs and go back to the coil.xml file and comment the nonlinear part. So now we're not adding the nonlin IDs tag, we're only using the linear portion of the material definition. We can leave the nonlin list as it is because we're not connecting the material with the nonlinearity. So now this is the linear solution. Let's simulate it. CFS coil. And it should also have been a little bit faster, since we only needed one iteration for the linear problem. So here we needed CPU time. Let's compare the wall clock time, 0.9, and for nonlinear simulation we needed 2 seconds. So twice as much time for the nonlinear iteration, a nonlinear simulation, than for the linear simulation. Now let's qualitatively compare the two results in PowerView. Let's open the linear solution first. Uncheck the boundaries. Flux density. So it looks quite similar in the first glimpse, but we see a difference in the maximum amplitude of the magnetic flux density. Now let's open the nonlinear result, coil nonlin, uncheck the boundaries, choose the magnetic flux density as the quantity to display, and make the linear result invisible. So now we're only considering the nonlinear result, and let's rescale to the nonlinear result. Click rescale to data range, and now we can see that the whole field in the nonlinear portion or nonlinear region here is decreased a little bit. We will consider, or we will experience this effect more severely in the eddy current problem, where we have severe boundary layers, and in the nonlinear material, the boundary layer gets a bit larger than in the linear version, because we're reaching saturation. And even if we increase the current, we won't get much higher flux densities because we're reaching saturation. Maybe we can try that, but first of all, let's check which region we are using. We're reaching saturation. Therefore, let's plot the pH curve again. Plot pH.fnc, and okay, we will reach higher flux density values, because here in our current simulation with the current excitation of 40 amps, we are here in this region. So we can actually increase the excitation. We can increase the current, and maybe let's try to double the current, the excitation current. Let's say instead of 40 amps or 40 microamps, now here 40 amps, let's say we want to have 80 amps. Simulate it again. CFS. No, sorry. We have to switch on the nonlinearity. And simulate the coil XML. We will experience a larger simulation time because we will probably need more iterations in order to converge. Like converge under brackets, we need to reach our stopping criteria. Okay, now we see we needed 5 iterations. And let's check the flux density values. Let's delete this file and reload this file. This is now the nonlinear. Okay, let's open it again. This is the nonlinear simulation now. Look at the flux density, and now we're reaching 2 Tesla. Is it nonlinear? It's nonlinear. We are reaching 2 Tesla, and if we increase the excitation current even more, we won't get much higher than 2 or maybe 2.1 or 2.2 Tesla, because we're reaching the saturation regime. Where is it? Here. Because we're reaching the saturation measure regime where the permeability decreases drastically. And what we also see is that the flux density is more homogeneously distributed over in this region here, which is also due to the nonlinearity. So what's important to mention is that each element here has its own permeability, because this element, for example, where we're reaching the maximum or kind of the maximum saturation of 2 Tesla, has a permeability, has a very small permeability. The region here, for example, the blue region where we have very small values of the magnetic flux density, so we're somewhere here in the linear region with a different permeability than here. This is important to mention. So in this case, we have a space-dependent or solution-dependent permeability, and it's not the same permeability for the whole region. That's the important part. All right, that's it actually regarding this demonstration example. And now let's have a brief look at the homework, at the new homework. Therefore, let me just stop the recording.